Hello everybody and welcome. Welcome to this ODiSI webinar. Thanks for joining us. We are very excited to announce the release of ODiSI version 4, which includes a new feature called Finesse. Hopefully you will learn something new today. So this is today's agenda. After a short introduction on ODiSI by myself, we will have Pat Connolly, who will present the new developments on ODiSI called Finesse. I will then present an example of ODiSI inversion using Finesse. Keegan Benalak from Segal will talk about how you can use the ODiSI result to help your geomodeling. Then we'll have 15 minutes available for Q&A. So first, a little bit of housekeeping. This shouldn't be new for us as I think now all are very familiar with virtual conferences and webinars. If you have any question during the presentation, please use the chat or question tab. The chairman, myself, will then select the questions and ask them to the presenter at the Q&A session at the end of the webinar. Just as a note, today's presentation is recorded and will be shared on Segal YouTube channel. So, before giving the control to Pat Connolly, I will take just a few minutes to summarize what is ODiSI in case some people were not so familiar with the technology. So first, ODiSI stands for one-dimensional stochastic inversion. It's a transparent and innovative approach to seismic inversion, which was initially developed by BP and is now productized by Segal. It's a Fascist-based inversion that jointly estimates facies, reservoir properties, and their associated uncertainties. It captures all the prior knowledge about a given field, prospect, or reservoir. ODiSI inversion runs by matching a very large number of pseudo-well realizations simultaneously to multiple angle stacks volumes. On the right-hand side, here, you can have a look at one of the typical outputs, here, the V-sand. The inversion problem can be defined as a solution space, which is our prior probability in Bayes wording. ODiSI will sample the prior by creating synthetics based on rock physics models and compare the sample to the data or seismic and accept or reject the sample based on a quality threshold. The quality threshold for ODiSI is a RMSE, root mean square error. The selected sample, here in yellow, can then be represented in the same solution space. It's our posterior probability, which is narrower than the prior. The prior knowledge is all information we have and need to use to create meaningful sample. So we can have well logs, vertical statistics, raw property correlation, geological model, stratigraphy, and so on. We compare, and using this prior knowledge, we create samples, we compare to our seismic, our data, and at the end we have our posterior, which is our characterization. Samples are pseudo-well realization. It all starts with the stratigraphic profiles, created using a time Markov chain using two matrices, bed thickness and transition from one facies to another. Those matrices are created using all the prior information, so well log, geological knowledge, and so on. After the creation of the stratigraphic profile, the full suite of log is created using the rock physics models, and everything is constrained by the prior. This slide summarizes the process of ODiSI. Our seismic input is an EEI chi projection. So EEI stands for Extended Elastic Impedance. For each trace in the volumes, ODiSI creates thousands of pseudo-well, typically 10,000, starting with a stratigraphic profile and then creating the full suite of log needed for the creation of the EEI chi synthetics. Each pseudo-well synthetics is compared to the seismic trace and either selected or rejected based on the RMSE value. The 100 with the lowest RMSE values are selected. For those 100 selected, each synthetic corresponds to a pseudo-well realization containing all the different properties, V shell, VP, VS, and so on. Those properties can then be averaged, which give us the outputs. Fascist probabilities, but also all the other properties with their associated uncertainties coming from the variation within the 100 best match pseudo-L. So here we have the probable list of Fascist and the V-sand. ODiSI gives two types of outputs based on the number of best match pseudo-L we average, meaning synthetics that all look alike, but can be created from slightly different lithology columns. So first, we have the average of the 100 best match pseudo-L. This is the result of the main inversion. But because now we have 100 best match pseudo-L, we can order them by whatever property we want. We can order them, for example, by an increase of V-sand. Then we can, if we want, average a subset of this 100 best match ordered by V-sand. It's what we call approximate percentile. This allows us to analyze the variation within the 100 best match pseudo-L. So for example, if we average 20 best match pseudo-L centered around the 10th trace, it's what we call the AP10. If we do the same around the 50th trace, we call it the AP50. And around the 90th trace, it's what we have then the AP90. If we zoom a little bit more on the outputs, we can see the difference in sound proportion. The tracks in the rectangle, so here, 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 and here, are the Fascist proportions result for the different cases. Those outputs are all possible solutions to our inversion problem, and it's important to be able to understand and analyze the variation within the best solutions. For each type of output, so 100 best match pseudo-L and approximate percentile, ODiSI can create volumes for each Fascist probabilities, probabilities of Fascist, V-sand, VP, VS, and so on, all the properties. ODiSI can also create maps like V-sand average maps. Another type I find very useful is the map of probability of finding a selected Fascist bed thickness greater than X milliseconds. In a recent project, we created a V-sand average map for the main reservoir and a map of sand bed greater than 10 milliseconds. In one area, the average V-sand was quite high, but the probability of finding sand bed thicker than 10 milliseconds was very low. This was due to a high probability of finding a lot of thin sand beds where the client expected a more thicker and homogeneous sand. That's all for me for now. Now I'll give the control to Pat Connolly, who will present to us the latest development for ODiSI Finesse in a talk called Climbing Mount Probable, Finessing the ODiSI Algorithm. For the few who don't know Patrick Connolly, he is a consultant geophysicist specializing in seismic reservoir characterization. He retired from BP in 2015 as senior advisor for geophysical analysis. His primary occupation now is providing training courses for the industry. He is also a visiting lecturer at the School of Earth and Environment at the University of Leeds in the UK. So let me change.
Okay, thanks, Lisa.
And we can see your screen, Pat.
Okay, and I've turned me on as well, so hopefully you can see me. Okay, good morning, everybody. So as Lisa said, my talk, Climbing Mount Probable, Finessing the ODiSI Algorithm. So as Lisa described it, ODiSI is based on a broadly Bayesian framework. And some of you may know quite a bit about Bayes' theorem, and some of you perhaps less so. But it turns out that probably all of us have got a better intuitive feel for Bayes' theorem than we might imagine. I'm just going to turn my screen off because I've got a huge picture of me right in the middle. It's really distracting. Sorry. So because it turns out that we all actually have Bayesian brains. So what does that mean? So if we consider visual perception, how does that work? Well, the conventional view would be something like this. There's a world out there. Light enters your eye from the world and it creates an image on your retina. And that image is transmitted to your brain. and your brain kind of sees the image and creates a model of the 3D world inside your brain based on that image. So that's a conventional view with information flowing from left to right. But as long ago as the 1850s, very clever Hermann von Helmholtz, physicist and physician, realized that that couldn't possibly be what actually happens, because your eye does not create enough information to do that. So he came up with an idea of unconscious inference, realizing that your brain must actually be doing a lot more of the work. And modern brain scanning methods have now actually indicated that the most information flows the other way. There's actually more information going from your brain to your eyes than the other way around. So what's going on here? So visual perception is now viewed, as it says here, a classic example of an ill-posed problem, which essentially means there's not enough information, not enough data, information in the data to solve the problem. So the human brain uses a method called predictive coding. And that works by first creating an image in your brain based on prior sensory information, a lot of prior knowledge. For example, there's an image of mountains and lakes, and it kind of you know that lakes are at the bottom of the valleys and the surfaces are flat. And if there's black and white things in the fields, they're probably cows, all this kind of stuff. And also a lot of tricks. For example, light from above Bayesian prior assumption. If in the absence of any other information, we assume that the light is coming from above. And I've used that trick in this panel down the bottom here, which hopefully you will see as a recessed panel. Obviously, it's not really, it's just a trick performed by the shading there. But it just kind of reveals that light from above Bayesian prior assumption, which we're not born with. We learned that apparently as a child. 3-year-olds don't have that. You don't develop it until you're about 12 years old. So based on that image, the brain makes a prediction. It prioritizes what it wants to know. It sends a prediction to your eyes, asks your eyes to check out the prediction. So your eyes evaluate that prediction, and the eyes then return the prediction error back to your brain. So what we can now see is that the role of the brain really is to minimize prediction errors. That's essentially what it's doing. It's creating models, making predictions. Your sensors test the predictions, feedback the prediction error, and then the whole thing goes in a loop, attempting to minimize the prediction error. And we can say something very similar happens if we're just doing qualitative interpretation. Here's a seismic section. There's not enough information on that seismic section to tell you what the geology is. We know that. You have to do a lot of work. But not only that, you need a lot of prior knowledge. So, a geologist looking at this has got lots of geological models in her head from all their training. And essentially what she'll be looking to do will be to test those models on the data. So she'll approach it with quite an informed prior. Maybe she's got, several models which she's testing. And as she works through the interpretation, making maps and evaluating, she'll kind of narrow that down onto a preferred model. And that's an enormously powerful process, as we know. People like me, it doesn't work so well because basically I don't have all that formal geological training. I'm kind of vaguely aware there's some rocks involved here, but otherwise my head is kind of full of EI equations and wavelets and things like that, which kind of doesn't work so well. So I'm going to need to, use a computer to help me out here. And more broadly, I think clearly there are limits to how far you can go with qualitative interpretation. If we want to really assess the quality of or the meaning of the amplitudes and ensure that our interpretation is completely consistent with the seismic data, then we're going to have to, use a computer to help us out with this. But essentially what that means is we need to get this prior information out of the brains of the geologists and into the computer. And that's what ODiSI does. It starts off with a geological model, from which you can derive things like our expectation of the facies, the proportions of the facies, the vertical statistics, and just as Lisa described, from that we can come up with potential facies vectors, huge numbers of them. There are lots and lots of possible models. We assign elastic properties to them from our petroelastic model. We build synthetics, and in the case of ODiSI, we select the facies vectors which provided the lowest prediction error. So again, the whole process is all about minimizing prediction error. We finish up with a full model at the end of the day, which with the minimum prediction error that we can find. So, and that's described as a set of facies vectors. But we recognize you know, that there's not a unique solution. So we don't have one Fasces vector, we have many, typically around about 100. And we use those, as Lisa described, to define the uncertainty of the posterior. And those Fasces vectors are typically averaged to come up with Fasces probability curves. They can match the well, something like that, so they're equivalent to a smoothed Fasces log, something like that. And we just got to work our way through the data in that way. So visual perception and sizing inversion are both ill-posed problems. We need some prior knowledge to obtain a solution. So the broad process is to build an internal model, make predictions, test them against the data, update the model, with the overall aim of minimizing prediction errors. Now, the next question, though, is, you know, can we improve that process? What can we do to make it better? You know, if we look at this example over here, a set of synthetics, so the left-hand trace is the data trace. The second one in is the average synthetic, which is a reasonably good match to the data trace. And these are all the individual synthetics. And they're kind of okay, but you know, you look at them and some of them are a little bit ragged, to be fair. Now, I think in this particular example, we didn't use a particularly large number of pseudo wells. So I think, you know, within existing ODiSI, we could have done a bit better than this. But you know, there's still clearly room for some improvement. So the challenge we've made ourselves is, how can we improve this? You know, how can we improve the ODiSI algorithm? Essentially, how can we provide ODiSI with a pair of binoculars just to get a better view of what's going on? So to do that, we're going to have to go into some depth, understand the problem in more detail. And in particular, we need to understand the nature of the posterior distribution. What exactly does this thing really look like? What are the characteristics of it? So to help understand what it looks like, what I'm going to show here is a random walk through the objective function. So the objective function, as defined, is going to be a measure of the predictability between the synthetics and the data trace, and that's going to be directly related to the final posterior distribution. So I start with a random Fasces vector. I'll start with the model. I'll start with the model over here, and here's its associated data trace. And then I pick a random Fasces vector, nothing to do with the model, just completely random, create its synthetic, and I measure the predictability between the synthetic and the data trace. And then I flip one Fasces sample, one millisecond sample. So this is a 50 millisecond Fasces vector sampled at 1 millisecond. So I flip a 1 millisecond sample. So that's the smallest step I can possibly make. And I repeat that 10,000 times. And this is what you get. This is now the predictability measured from, you know, one step at a time through the objective function for 10,000 iterations. And here it's zoomed in on the first 1,000. So what can we see from this? I get, you know, there's a few takeaways from this. I mean, it jumps around an awful lot. It's not a smooth surface at all. It really does jump around quite a bit, which implies that changing one Fasces vector, one millisecond sample, sorry, one Fasces sample, can make quite a big impact. And if we look at the distribution of predictability differences, how much predictability changes from one Fasces vector to the next, we can see it's up to plus or minus 0.1, which is quite a significant change in the quality of the match. Just for reference, the predictability of 1 is a perfect match. The predictability of 0 means that your residuals are equal to the energy of the data trace. The other takeaway is looking at the average values of the predictabilities. We can see the average is somewhere around about 0.2 to 0.3, which is, you know, a very poor match, as we'd expect, because we make no attempt to optimize the matching. It's just purely random, so we'd expect most of the matching to be poor. But every now and again, purely by chance, we hit upon a Fasces vector, which actually is a reasonable match. We're getting up to kind of 0.7 around here, and 0.7 is not bad. You know, it's a kind of a tolerable match. So if we look at the distribution of predictability values shown down here, we can see the mean somewhere between 0.2 and 0.3, maxing out somewhere a little bit above 0.7, between 0.7 and 0.8. The other interesting thing is how well it actually fits a Gaussian distribution. It's an extremely good fit to a Gaussian distribution, and we can exploit that, as I'll show in a minute. So what this allows us to do is to predict the proportion of Fasces vectors with a predictability above any given threshold. Now, just to be clear, that distribution was based on 10,000 samples. That's still quite a pretty big sample, but the total population is 10 to the power 15. That's the number of facies vectors that you could construct from a 50 millisecond interval at 1 millisecond timing. So 2 to the power 50, basically, 10 to the power 15. So the sample space we're dealing with is truly huge. It really is very large indeed. But if we just go along with this and assume that the Gaussian distribution is a reasonable approximation to the true distribution, we can make a few observations. So this table shows the proportion of facies vectors having a predictability above some minimum threshold value. So 0.6 predictability is kind of the threshold for what you might consider to be, an okay kind of match. It's not a great match, but it's kind of, more or less things are about in the right place. And what it says is that 1% of all the facies vectors have this predictability, which is a huge number. 10 to the power 13 facies vectors have got that degree of predictability. If we increase the threshold to 0.8, then we're at 0.5%. Sorry, 0.05%. And 0.8 really is a pretty good match. You'd be quite happy with that for most applications. And if you really push it to 0.9, you can hardly see there's any difference at all between the synthetic and the data trace. And there's 0.01% of facies vectors have this quality of match. But that's still a huge number, 10 to the power 11. So, over 10 billion facies vectors with a predictability of above 0.9. Now, those numbers may not be quite right because we're not quite sure that it's exactly a Gaussian curve at the extremes here. But, even if it's out by several orders of magnitude, it still gives us a pretty good idea of the numbers involved that we're dealing with here. So here's our predictability. Now, predictabilities are not probabilities, though. So we can convert predictabilities to probabilities. That's a subjective transform, though. So predictabilities are a measurement. Probabilities are a subjective assessment. So I think what we could say is that, a predictability that's certainly less than about 0.5, the probability that would be incorrect is essentially 0. Anything with that bad a predictability just can't be considered a match. And clearly, when you get up to 1, well, above 0.9, the predictability is almost 1, I think. So the probability would be about 1. So the transform looks something about like that. The transform between predictability and probability. So this is a logistic function, which appears to be doing the right kind of thing. And if we apply this transform to those predictabilities, these are now the probabilities. So these, remember, now are the probability of each facies vector being a match to the data trace. And what you can see is for the vast majority, the probability is essentially 0. They just don't match. But there are, a few out there which have got reasonably high probabilities. They do appear to have predictabilities which are good enough to be have a high probability of being a good match. But you notice that they're just isolated spikes. This is not sort of a gently rounded sort of landscape, rolling hills or something. These are isolated spikes, implying that just a few changes to the facies vector will change the match from something acceptable to something not acceptable. So there's this kind of a surface out there, and we can envisage it as being something looking a bit like this. I've called it, to me, this looks a bit like a sea urchin, so I call this a geophysical urchin. But of course, in this case, it's got more dimensions. It's not 3 dimensions, it's 50 dimensions. So you have to picture a 50-dimensional sea urchin. And that is the thing that we're dealing with. That is the shape of the objective function. In the jargon, we'd call that highly non-convex. And it really is challenging. I mean, seismic inversion is a really, really difficult problem because we're dealing with objects like this. And this is clearly going to be a challenge for any algorithm to deal with this. So, in summary so far, each spike is a solution, but the spikes are really narrow. They're very sensitive to small changes in the facies vector. So this is a spike in predictability space, and this is a spike in probability space. So you can see there's, we can flip one facies vector and it's still okay. Flip one more and we're kind of losing it, and we flip the third one and it's just dropped off the cliff. Very, very sensitive. And remember, there's about 0.01% of all the facies vectors have got this really high predictability, about 0.9. So that would imply that if we wanted to find 100 of them, which is kind of, what we're trying to do here, remember, is we're trying to find a kind of representative sample, an unbiased representative sample of facies vectors, which we can then assess the overall probability or the overall uncertainty of predictions. So typically we like to find around about 100. If we can find 100 unbiased facies vectors, that will give a very, pretty good representation of the uncertainty. But the statistics which I've shown here would imply that we'd need 1 million pseudo-wells to find 100 with predictabilities above 0.9. And that's, the runtime is just going to be, too excessive for those. We can get up to like 20,000, okay, but we're kind of still, good order of magnitude off for what we'd like. So can we use smarter algorithms to get around the problem? So essentially what we're doing, we picture our 50-dimensional sea urchin, and essentially what we're doing is we're throwing darts at this sea urchin and hoping to hit the exact edge of, the peak of a spike. And, as you can imagine, that's going to be pretty difficult. So, here's a spike in predictability space, and the chances are that even the best darts we throw are not going to quite hit the point of the spike. They're just going to come down somewhere on the flank, something like that. But if we find a pretty good predictability, something above, 0.5, saying 0.6, 0.7, the implication is there's quite likely a spike nearby with a much higher predictability. So this suggests we could locally optimize each of these solutions. And we can do that by making very small changes to the facies vector. So if we look at these facies vectors on the right, the left-hand one has got a predictability of 0.55 with a data trace, which is poor. That's not a very good match. But you can see by making very, very small changes, I mean, it's really hard to see the changes from one to the next. All I'm doing is flipping a single facies vector code. I can rapidly drive up the predictability and get up to 0.8 pretty straightforwardly. So essentially what we're doing is we're moving up to the top of the spike. So this is where the climbing Mount Probable bit comes in. So we're climbing Mount Probable up here. Some of you may remember that this title I pinched from a book by Richard Dawkins called Climbing Mount Improbable. And coincidentally, actually, that was much concerned with how seemingly improbable structures, such as a human eye, could evolve over a period of time by small incremental steps. So he was pushing the kind of the improbable nature of the final result. But actually, in our case, we're actually trying to find something which is highly probable. We're looking for the most probable outcomes, not the most improbable ones. So how well does it work? So here are a set of facies vectors and associated synthetics from what I'll call ODiSI Classic, the current algorithm. And if we run this local optimization, this is now what we get out. So the local optimization, as Lisa mentioned, we've called Finesse. This is a new set of facies vectors, and this is the new set of synthetics. And it's obvious, you can just see straight away what a dramatic improvement that this process has made. All of a sudden, the individual synthetics are now a much better match to the data trace. So this has really made quite a significant improvement. Now remember, what we're not trying to do is we're not trying to make all these facies vectors look the same. We're not searching for some global optimum solution, because that doesn't exist. We know there are billions and billions and billions of solutions out there, and we're not trying to find one of them. We're trying to find quite a lot of them. So we're only trying to locally optimize each of those solutions. We're not trying to jump around and find some global solution. So we want to retain the diversity amongst this set of facies vectors, which we've done. I think there is still a lot of diversity in here, but all of these now provide a much higher quality match to the data trace. If we think about prediction errors, so here's our input data for that data set. It's a simultaneous inversion in this case with a chi-15 and a chi-90. Internally, we build a synthetic model, so this is the average of the synthetics, and you can see, visually it's a pretty good match. Now with ODiSI Classic, these were the size of the residuals, which is not bad, to be fair. Certainly the chi-15 residuals, it's not bad. The chi-90 is maybe a little bit higher, but it's tough getting the residuals simultaneously down for both. But after Finesse, you can see we've now managed to drive down the energy of the residuals quite a bit more. So this is the whole, remember the whole objective we're trying to set is to minimize prediction errors, and that's what we're doing. We're minimizing prediction errors. And how does the section look? So here is the section view. ODiSI Classic, so this is a turbidite field, so these are turbidite lobes, clean sands down here. And after applying Finesse, you can see that we get a much sharper image. And in particular, we've now got coherent events representing the shady sands, which were kind of really absent before. And of course, the well ties are very good. So it appears to work really well. And Lisa's got another example, which she'll show afterwards. Right, I just want to touch on another upgrade, which has been included in the last ODiSI release. So going back to priors, we know we need priors, clearly, to come up with a solution. But sometimes, we don't get the priors right. Putting in the priors is a very subjective process. You're trying to do the best you can with whatever knowledge you have from the geological model, but it's inevitably subjective, and sometimes you might get it wrong. And the same applies for vision. We've got all these tricks, which I mentioned earlier on, the light from above prior, and sometimes those tricks are not appropriate and they don't give us the right solution. So, for example, look at this image on the right. What does it look like to you? It's a surface. Is it solid or liquid? It doesn't really look like a liquid. It looks kind of solid, maybe a solidified lava flow, perhaps. But if we flip it upside down, now what does it look like? So it's actually a very familiar image, just the surface of the sea. And yet when it was upside down, we didn't recognize it as an upside down image of the surface of the sea. We saw something completely different. And that's because in that particular case, those prior tricks were not working for us. They were misleading us. So how can we go about separating out the effect of the priors from the data itself? Because sometimes that's really useful to be able to separate the priors and the likelihood information. So we can just check and test what the priors are actually doing for us. And in the case of vision, there is apparently a way to do that. According to a report which I saw a couple of weeks ago, you take LSD. If you take LSD, it switches off all the prior information and you just get the data from your eyes coming straight at you with all sorts of weird stuff going on. So not recommending that, but that's apparently how that works. In the case of seismic, it's going to be particularly useful because the impact of priors is highly variable. And that's because the information content of seismic amplitudes is itself extremely variable. So if you look at a section here, it's a high quality section, offshore Angola. It's a gradient color inverted section. And you can see there are two reservoir intervals, sheet sand at the top, channelized sand down here. Same rock properties, same data quality. And yet the information content of this sheet sand is way higher than the information content of this channel sand. And that's because for two reasons. It's thinner, so all the frequencies you need to define it are within the seismic bandwidth, and it's only got a simple mix of two phases, just sand and clean sand and shale. Whereas down here in the channelized sand, it's just beyond that threshold where we don't have enough low frequencies in the data to define the full thing. It's about 70 or 80 milliseconds thick. This is not a broadband data set, so the lowest frequency is kind of around about 10 hertz. So we don't have wavelengths adequate to span that interval. So the uncertainty from the lack of frequencies kicks in, and there's also a more complicated mix of phases because we've got a lot of cemented sand in the mix as well. So consequently, for the upper layer, the impact of priors is quite minimal. You can stick in any old priors, as long as you say the sand and shale, it's going to come up with a good result. Whereas for the lower unit, getting the priors right is really quite important. Otherwise, you're going to finish up with the wrong answer. So what we've put into ODiSI is a way of explicitly outputting the likelihood itself, we're excluding it from the priors. So how do we do that? So the prior information is just the average of all the pseudo wells. So if you average all 10,000, 20,000 pseudo wells, the facies vectors of them, this is what you'll get. So these are the proportions, the mean proportions of the three facies, in this case, oil sand, shale sand, and shale. And these are the standard deviations of those three facies. And also, if we average the accepted samples, the best matched pseudo wells, then that gives us the posterior distribution. So again, the mean of the facies proportions and the standard deviation here. Now, we know that the posterior is proportional to the likelihood multiplied by the prior. So using advanced mathematical techniques, we can deduce but the likelihood is going to be proportional to the posterior divided by the prior. So that's essentially what we do. We divide the posterior by the prior to come up with what we call the explicit likelihood. Now, it's not quite straightforward as that, actually, because it's a slightly unstable calculation, so you actually have to do a little bit more work than that, but that's the principle of it. And what we can now see is the likelihood. This is now isolating the information that's coming from the seismic and not affected by the priors at all. And if you kind of get your eye, you can see the effect of the priors. It kind of bumps up the probability of there being clean sand in this lower reservoir unit down here relative to this one. And it bumps down the likelihood of this or the probability of this clean sand up here, and so on. So the priors are adjusting the likelihood probabilities as we expect. You know, that's what we want the priors to be doing. But it is sometimes helpful just seeing exactly what comes out of the data, not being impacted by the priors. So in section view, these are our prior facies probabilities, mean and standard deviation. These are our posterior mean and standard deviation probabilities, and by dividing one by the other, we can now get the explicit likelihood. So this is now the information that's coming from the seismic amplitudes. And this is a pretty limited section in here, but I think, you know, on bigger, more interesting sections, you know, it'll be quite illuminating to see what information is actually coming from the seismic, and in particular how uncertain it is, because in some places the level of uncertainty is going to be extremely high. Even on, you know, as I said, even on high quality data, you can still get very, very high levels of uncertainty if the facies mix is too big or the interval thickness is too high. So, okay, so that brings me to the end. So just in summary, visual perception, qualitative interpretation and probabilistic inversion all use broadly Bayesian processes, with their overall objective trying to minimize prediction errors. And we've now found that we can significantly reduce prediction errors even further by using a process called Finesse, which basically is one of the localized optimization. I've also shown that we can calculate the explicit likelihood to distinguish the contributions of the data and the prior. Okay, so thanks for your attention, and I'm going to hand back to Lisa now, and I can pick up questions at the end.
Thank you very much, Pat. It was a very interesting talk. So now that we're all very familiar with the theory of Finesse, I will show you some results on demo dataset. So Finesse was utilized on multiple projects for several legal clients with quite great success. Unfortunately, I'm not able to show those data. So today, I will only be able to show you some results on one of our demo datasets. This demo project uses two chi projection, one chi minus 90, which is the lithology angle, and the chi 15, which is the fluid angle. So, thanks to the multiple QC and cross plots available, we are able to display the 100 best match pseudo-well for different properties before and after Finesse. This slide presents the 100 best match pseudo-well for the lithofascious realization before Finesse here and after Finesse. So we can see for the lithofascious that we have now a better continuity within the 100 best match pseudo-well. If we look at the synthetics, you can see that for the chi minus 90, the Finesse result show a much better match and less variation, which is what we want. We have a very similar result for the chi 15, so way less variation within the 100 best match. After looking at some results at the well, we can now have a look at the differences between before and after Finesse on 2D lines. So this first line, is a probable lithofascious outputs, and it presents the winner of the Bayesian classification. The darker the color is, the stronger the probability of having this fascious is. ODiSI can also output the probability of each fascious, but today I will only show you this probable lithofascious, the combine. This is line 1, and this is the result before Finesse. Just as a note, the well here, well A, is displayed as a QC. For the inversion, ODiSI doesn't use the well or doesn't try to fit the result as well. In effect, all wells are blind. The wells are just used for the creation of the rock physics model and to help with the statistics parameterization. On this line, in the reservoir section, so between those two surfaces, we can observe some uncertainty, especially in the shaly area, where we can see that the color is lighter compared to this darker color here on the over and under burden. This is because we have more uncertainty in those areas compared to the over and under burden. So this is a result before Finesse. And now this is after Finesse. So we clearly see that the Finesse algorithm has good results. Finesse helps a lot in refining the result where we had previously a lot of uncertainties. So both in the shaly area, but also in the sandy area. So let me flip a little between before and after Finesse. So before and after. We can also have a look at a second line. This is again the probability of Fascist before Finesse, and this line is approximately perpendicular to the previous one. So we still have our sand, but again a much or less darker color in the shale area. And after Finesse, we have a much better and stronger result. So before Finesse and after Finesse. So Finesse has been able to give us a better and more refined result on the probabilities of Fascist. Finesse was used on several Seagull client datasets as has proven to improve the probabilities of Fascist as well as reduce significantly the residuals. Again, unfortunately, I'm not able to show you those data today. So now, our next and last talk will be given by Keegan Benalak from Seagull, who will talk about how you can use ODiSI results to help your geomodeling. So Keegan was trained in marine and petroleum geoscience. A brief stint in academia was supplanted by a dive headfirst into the darkest of arts, subsurface software development, and, darker yet, commercialization. He spent several years managing solution projects aimed at addressing shortfalls in the spheres of geospatial mapping, geostatistics, and uncertainty analysis in static modeling for various companies, including Shell and Baker Hughes. He now thoroughly enjoys his role as a technical account manager with the Seagull team, albeit rather frustratingly from the confines of his desk in his lounge. So let me give you the control, Keegan.
Thanks, Lisa.
So now you have the control.
Good. I'll just share my screen. Can you?
Yes,
can you
we can see your screen. Yes, we can see your screen.
Good. Can you see the little control panel?
No.
Good. 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 Thanks, Lisa. So my name is Keegan Benalak. Yeah, so I've been tasked with giving a few closing remarks on the more conventional aspects and approaches involved in putting our ODiSI results to use in our reservoir modeling routines. Yeah, so this is a presentation I gave the last ODiSI UGM. It's not specific to the Finesse process. It's more of a sort of general assessment, but it's a nice little way to end up the session. So, quick notes in the agenda. I'll cover this in 3 parts really. We'll start briefly with a few reminders of the practical aspects of using ODiSI data and where they can add value. After that, we'll investigate a few key techniques for preparing the ODiSI outputs for use. And then once we've covered that data prep, I'll get into the nuts and bolts of how we can use the prepared data to steer our modeling routine. So again, there's 3 focus areas for that. So the first point, and maybe not directly applicable for this presentation, probably, but arguably as important, is that the ODiSI workflow helps us take a more holistic view of the subsurface, because its implementation requires input from really the full spectrum of geology stakeholders. And so invariably the first few weeks of any ODiSI project, keeping in mind that we run this typically as a bureau type service, is spent assessing things like seismic and well data quality and the key uncertainties in our workflows, I guess, like the quality of our well ties and suitability of rock physics models and positions of fluid contacts or fascia definitions. So It gives us an upfront chance to calibrate at a multidisciplinary level and to ensure consistency in our approaches, and that's really the key piece of value when starting these out. The second point and the key value leverage from ODiSI in the context of my presentation for today is that it gives us critical insights into the spatial distributions of lithofasces and net intervals away from the ground truth. So this is clearly valuable in answering fundamental questions about our reservoirs, like, you know, the sand body morphologies away from well control, or the nature of connectivity between wells and the distribution of shales and baffles and barriers to fluid flow. So if used carefully and in conjunction, you know, with curated understanding from things like conceptual models or core where available, well logs and analog data, ODiSI can provide us outputs needed to construct robust and reliable fasces models in particular, and that's what I'll focus on today. So some quick reminders: ODiSI produces a collection of seismic data sets in the time domain. This might sound obvious, but typically we model geology in the depth domain, so there'll have to be some sort of jiggery-pokery to get the data ready for consumption. Secondly, there's a significant discrepancy in scale. The typical survey has voxel geometries on the order of 12 to 15 times smaller than the horizontal than grid cells, while the vertical is kind of the inverse. You know, we tend to have much thicker voxels than we do geocells, usually at a ratio of about 1 to 5. So it's going to be some sort of, you know, there's going to be a need for some sort of workaround or resampling to accommodate for the scaling problem. Number 3, the results from ODiSI are probabilistic. The principal volumes of interest for fasces modeling are the fasces probability volumes and to a lesser extent the net to gross volumes. I won't get into the philosophy of modeling net to gross today, but in short, outside of volumetrics, I personally don't believe it's necessary. So, and then the fourth thing is there's a strong dependence on the quality of the data input, our assumptions and interpretations. At the end of the day, ODiSI is a complex model based on interpretations and input data, and it's matched to our seismic data. So the seismic, for example, doesn't have a low frequency content to image thicker reservoir units, and you can't expect to carry over any meaningful results into the modeling domain. So let's go through some of the fundamental approaches to reading the data for use. I'll touch on 3 here, but particular suggestions in the chat box if you like. So option 1 is to resample our individual fasces probability seismic volumes directly into our geomodel. And in Petrel world, this was achieved using the seismic resampling process in the geometrical modeling tab. So yeah, the process effectively allows seismic voxels to be averaged into the geocells, with the outputs being the resampled p-lithofasces 3D model property in your grid. A couple of key sensitivities here are the choice of which seismic cells to average. We usually allow contributions from all intersecting cells weighted by intersection volume. There are other techniques, but they take quite a bit longer and they require quite a bit of caution. And the second thing is the choice of averaging technique. You know, because we have decimals ranging between 0 and 1 for the probability volumes, arithmetic averaging is typically appropriate, but we don't have to worry about more complex approaches like geometrical or harmonic means. So once you've sampled into the static model, these fasces probability volumes, for example, in this example here, the P shale or P clean sand, can be used in a number of ways, and I'll get to that shortly. And then just a key point is that in order to use the resampling option in a 3D sense, you'll have to depth convert your ODiSI seismic volumes. They are in time. Option 2 is to create zone-based fasces probability maps. Again, this is a straightforward sort of approach, and it can be done using the surface attribute process in Petrel. So the usual approach here is to perform a mean amplitude extraction from each individual probability volume, for example, P sand here, and extract it onto a target surface, with the output being a lithofasces probability map. And the benefit of that is extracting probability maps is a simple way to abstract the probability from the time domain and into a lateral trend, which basically means you can do an extraction on a time volume and then input that map directly into a depth model without the need for depth conversion. So the key sensitivity there is to mine the trace segment interval, which is the vertical range over which you average your trace amplitude. So I guess what becomes important there is to have the relevant zonation well defined to exclude any extraneous noise or data from your overall underburden. And the third option is to get stuck into direct statistical analysis of your ODiSI p-lithofasces seismic volume. So in particular here, we'd be looking at statistics on the fasces proportions themselves. You know, complex or not, most conventional routines rely heavily on fasces fractions provided either by yourself or directly from the well data. And it's usually a big point of contest. So the easiest way to interrogate or extract these trends, in my opinion, is using the Sigala Blueback Investigator. It's probably a bit of a sales plug, to be honest, but it's the easiest way in my opinion. I could take you through that in a separate session. And the key here is that these numbers can be used directly in most modeling routines when we specify the target fractions, which gives us the least alternative to complement or supersede our well-derived stats. So we've had a look at the 3 most common techniques to prep our data. The next few slides will focus on the 3 main areas in which to deploy these outputs. So regardless of the algorithm you're using, whether it's kriging, object-based, or one of the Gaussian methods, there's usually always 3 key inputs needed to build yourself a robust and reliable Fascist model, or should I say defendable. Firstly, we set about defining our variograms and our depositional element geometries, where we use object-based modeling, and these control the direction, orientation, and lateral extent of our Fascist populations. They also impart a sort of key influence on our connectivity in our models. And the depositional element geometries in particular give us our first tangible opportunity really to impart some geological reasoning into our model. The second thing we need to do is to define the Fascist fractions or proportions, which are obviously key to influencing the relative quantities of different Fascists across our studies. So these can be as simple as typed in numbers as a guesstimate. You can quite literally just type numbers in there, whatever you want. Has to be geological, obviously. Or they can be as complex as, precise, not necessarily accurate, but precise figures driven by neural nets based on attribute blends, which I've seen being done in the past. And then finally, and arguably the most important, is we need to define our general Fascist trends in all axes. These obviously influence the logical spatial positioning of our different Fascists. So basically, where each Fascist type is likely to be present in our study area. And really, this is our second opportunity to impart some realistic geological variability on the model. So in most cases, we derive our parameterization for these 3 components from analysis primarily of well logs and core data. We also like to use things like analog data or conceptual models and understanding of regional geology. But I think for the first time, really, ODiSI really helps us extract this information from the seismic in a way that I haven't seen being done in the past. So we'll have a look at these next. So step 1 is to create and optimize our variograms and depositional element geometries. Before I do this, I always start by asking myself a simple question. Can modeling an experimental variogram constructed from biased low sample rate datasets adequately describe spatial correlation in my study area? And the answer to that invariably is no. The data is just too sparse and too biased. But we do it anyway. I've sat through several debates centered around optimizing variance functions and fitting experimental variograms, but things like search cone parameters, optimal lag distances, tolerance angles always come up, but at the end of the day, it doesn't really matter. It's all wrong anyway. What matters is how we qualify the accuracy of the parameterization, particularly in the context of what the geology ought to be doing at the scale of our observations. And this is where ODiSI is really powerful. It provides us a yardstick in 3D and 2D and a way of gauging your accuracy in the parameterization of your variograms by allowing you to, 1, qualitatively QC your variogram through visual comparison of your output results. So taking your model in the 3D viewer, plunking that next to your seismic volume, your ODiSI seismic volume, and comparing the 2 together, your P with the Fascist volumes. And then 2, to quantitatively assess through more sort of rigorous measurements, things like azimuthal vectors and major and minor ranges. So you can basically take your seismic, your ODiSI P with the Fascist volumes and measure them with things like the Blueback ruler and try get a bit more of a handle on the data that way. So in specific cases, you also have potential to identify and describe specific depositional features like fan lobes and channels, which are used in object-based routines. And I've seen this. I've seen the geobody functionality of Patrol being used quite effectively for this. Second step is to define the appropriate Fascist fractions for our model. And here the starting assumption usually is for specifying a target fraction is to use well data statistics. But the diagram on the right, that histogram, which I showed earlier, gives us a little insight as to why this may not be an appropriate method. Obviously, the first question a reviewer in this case may ask is whether or not that's driven by targeted drilling or the geology. We are all in the business of drilling for oil, not rocks. So, in reality, well data is less likely to provide us a representative Fascist fraction. And sure, we can decluster these proportions. A lot of people favor declustering, but in reality, in my opinion, declustering isn't necessarily representative of what's going on the ground. So to compensate for this, we usually look to analog data and conceptual models. And these do provide an additional means of control, but they also have large associated uncertainties, and we all know about the problem of cognitive bias and anchoring. So QODiSI, an alternative way to control the target Fascist fraction is just use the probabilities that we generated from ODiSI volumes using the Blueback investigator. These arguably provide a more objective and more holistic assessment of the problem space, because at the end of the day, we sampled the entire volume with guidance from the seismic data. And looking back at our example on the right in the histogram plot, ODiSI data represented by the blue histogram bars presents quite a different story to that of the well-derived fractions in the red. So there are 4 ways to determine the target fraction within Patrol. Options 1 and 2 are sort of the standard log-derived methods. Option 3 is where it gets interesting. This allows the user defined manual fraction to be specified. So this is where you can use your Fascist statistics derived from your p-little Fascist volume, which you pulled out in Investigator. And then the 4th option is to extract stats directly from a trend. And in this case, you can actually use the resampled 3D p-little Fascist properties. But you can also use the probability map extractions too. And then the final step is to identify and impose where possible any trends. So, we can't hope to have a coherent, geologically consistent spatial distribution in our model unless we were able to exert some sort of geological influence on the grid. So trends are really key to achieving this. And looking back at the previous 2 steps, Fascist fractions provide the guideline proportions, and Variograms, give us a mechanism for populating our properties stochastically into 3D space. But the reality is that, geology is process-driven and presents itself in most cases as discernible trends. And so, in other words, it is by nature non-stationary. And so the aim of the game should be to impose this understanding of the geology on a model. And this is where the zonal Fascist proportion maps and resampled probability volumes from ODiSI are really powerful. The little Fascist maps in particular give us key information about where we might expect to find things like target lithologies. And these can be easily integrated through direct use as trends in the Fascist modeling process. So, as mentioned earlier, the advantage with the zonal trends is that they can be extracted on the ODiSI time volumes and then used directly as input to your depth geomodels, whereas the ODiSI volumes would need to be depth converted. Vertical scaling also becomes an issue with 3D volumes. Typically we use a VPC or vertical proportion curve generated through upscaling of our well data to better control the vertical distributions, particularly in the case of subseismic zonation. So those are the 3 techniques. I thought I'd round this off with a nice little illustrative example of the combined effects of using Variograms, Fascist fractions, and trends, all based on ODiSI outputs, just to sort of drive home the point. So at the top left, we have the raw, unprocessed ODiSI p-little Fascist volume shown for comparison, and we can see a definite sort of central belt of clean sands fringed by shaly sand in the background of shale. And we also have 2 wells, A and B, in the study. The second image in the middle is a Z-slice extraction of the resultant geomodel Fascist property that we built using our default variogram and Fascist fractions taken from the 2 wells. And you can see there really isn't a structure to the clean and shaly sands. They're principally kind of stochastic in nature with very little connectivity and organization. It's probably because the range in the variogram has been set really short. So for me, this is the classic variogram appearance. It's kind of mottled and disorganized. Kind of looks like a speckled egg, if you will. And then in the third Z-slice extraction, we start to see a strong convergence on the ODiSI inputs, and noticeably a more geological and defendable model, I would say. And this is because we've used the ODiSI inputs to parameterize our variograms. We've derived our Fascist fractions from the ODiSI 3D models, and we've used lateral trends in the form of the p-little Fascist maps. And in combination with that, we've used a vertical proportion curve to set the vertical components, and you can see straight away that high degree of connectivity, really coherent looking model. Looks quite nice. So yeah, before I go to the summary, I thought I'd just sneak in a bonus section focusing on the ODiSI inputs in more modern MPS workflows and multi-point statistics. And really, these are a family of stochastic routines quite common nowadays, actually, to be fair. But instead of relying on the variance functions rather than variogram, they rely on reproducing patterns from training images. And they do this while trying to attempting to honor the upscaled well data. So effectively, we replace the variogram in these routines with a training image, which provides tighter control over the spatial distribution and connectivity of our reservoir targets. And a key point with regards to ODiSI in this context is that the NPS workflows also rely heavily on the utilization of external secondary factors, which are usually used to control the proportions of Fasces. And we refer to these as constraining probabilities. So these proportion constraints can be controlled by vertical proportion curves, as I said, proportion maps, and probability cubes. And these things can be directly fed using the ODiSI lithophases maps and volumes as well. So quite powerful in that sense. Yep, so to finish, just ODiSI is a Fascist space inversion, which captures all the prior knowledge about a given field, prospect, or reservoir. It unlocks critical information. So I'm just losing my screen here. Aha, there we go. It unlocks critical information into a data set that may otherwise be hidden from more traditional data analysis routines. And it supports informed decisions, particularly in the generation of reliable Fascist models. Lisa, can you still see my screen? So I'm just sort of losing my screen now.
Yes, we can see the summary slide.
Okay, so it's kind of jumping all around on my machine. It's just gone off. In particular, it helps us to define our variograms, Fascist trends, Fascist fractions, and trends for our models. Obviously, the outputs require some massaging, but usually this can be undertaken with most basic of patrol functionality. So there we go. That's me. Thanks, Lisa.
Thank you, Keegan. So now it's our Q&A session, and we have some questions. So one of the question is, so I open to Pat. As one of the key input into the process, how important is to generate EEI volumes with close to perfect well ties? Pat, do you have any comment on that?
Well, nice. Yeah, I mean, well ties. I mean, obviously doing well ties is a crucial part of the process. And you should chase them down, and if they don't look good, you should try and understand why, etc. But at the end of the day, there are reasons why well ties may not be quite as good as you would like. I mean, wells are measuring different things at different scales and seismic data. Well data can go wrong, just as seismic data can go wrong. So I don't want to sound like I'm making a bunch of excuses, but I wouldn't be too obsessive, I guess, about ensuring that the well ties are absolutely pristine. You can still get plenty of really good results out without necessarily having pristine well ties. But that doesn't mean you don't worry about it either. I mean, you definitely chase them down and try and figure out if there is a problem, I think.
Yeah, and to be fair, it helps with the QC when you run 2D lines, if your well ties are good. So
yeah.
Is it better to use color inverted EEI volume, I suppose, to other method for doing the inversion, or to change domain from reflectivity to impedance?
Yeah, so that's a really good question. And actually, BP presented a paper at a conference earlier this year, I think it was, in which they've been doing some analysis on changing the input data type. And what they showed was that definitely color inversion is better than reflectivity. That's pretty conclusive. It just matches the bandwidth much better with the results. But the results they found actually was that combining doing both, they seemed to find better results still. So if they did a joint match to color inversion and reflectivity, they seemed to get even better results, which was quite interesting and perhaps not expected. But if you're just going to use one volume, without doubt, color inversion is better than reflectivity. Yeah, and we always expected that. So it's always set up just to use color inversion. That's we always only use color inversion for all the projects.
Okay. The quality of the EEI very much depends on the quality of the gradient. Is it better not to run ODiSI unless the data is well preconditioned? You want me to repeat?
Yeah, you're right. I mean, it depends what you're trying to get from the AVO information, really. How crucial. Sorry. Ooh. Sorry, can you hear me? Okay.
Yes.
Hello. I can hear you.
Hello?
You can hear me?
Yes.
Okay. We've got some delay on the line, I think. Yeah. So, I mean, it's a judgment call here. It depends on how much information is required from the AVO data. And what the quality of that AVO information is. As you know, if the AVO information is crucial, which it sometimes is, to distinguish between the different phases, then you really have to try and push it. And if the gradient data is of very poor quality, then there are times when you have to give up. Sometimes that does happen. So then it's just a balance. I mean, we have run projects. Lisa's run projects where we only use a conventional stack. Because the gradient was not good enough quality, but in that particular case, it was because it was not essential either. We could still get a good result without it. So again, it's one of these things that if you can get good quality gradient, clearly it's going to help. And quite often, the way it works is you'll find that you can go up to moderate angles. You can maybe go up to say 45 degrees, and then pushing much beyond that, then the quality degrades. So you can kind of get a limited range of angles, but maybe not the highest angles. So maybe it kind of precludes a lithology volume, for example, but you can still get an optimized fluid volume, that kind of thing. So it's very much a balance, depending on the requirement and the quality of your data.
Yeah, and in some cases, for example, I've used a far stack color inverted, which minimize the effect of the gradient because you don't have the gradient. So, what if you cannot generate a fluid angle even though you have hydrocarbon in your well? Personally, I never had this this situation. For me, the fluid angle is the one you always have. It's the lithology one that you might be trickier to obtain. What do you think?
Yeah, I mean, usually, even a far stack is a pretty good approximation to a fluid volume. So usually a far offset stack is kind of usually fairly reliable. Sometimes if you've got poor quality gradient, you may not be able to fine tune it. If the rock property analysis suggests that your your optimum fluid angle is say at 40 degrees or 35 degrees or something, you may not be able to get good quality projection at that angle. But falling back to a far offset is nearly always okay, and that's quite often kind of good enough to get good results, I think, as Lisa just mentioned.
Yeah. So given the sensitivity of predictability to the Fascist vector, is there a risk of being too focused on matching the imperfect seismic trace and thereby over-constraining possible outcomes?
Yeah, okay. I mean, there is. I mean, the uncertainty of the seismic amplitudes is obviously a concern. It's one of the uncertainties. How reliable are the seismic amplitudes? And the lack of reliability of amplitudes, as we've just been discussing, is actually typically driven by the quality of the gradient. I mean, usually if you just got a conventional stack, the amplitude is usually fairly reliable, I think. But the reliability of those amplitudes can degrade quite significantly if you're going up to high chi angles and your gradient data is not very good. So one thing you can do though is you can parameterize amplitude uncertainty in ODiSI, and the way we do that is you specify a chi angle uncertainty. So you'll say, well, I've got a volume at say 45 degrees, but I'm going to put a chi uncertainty on it of plus or minus 10 degrees. And what that will do, it would generate synthetics with a random distribution of angles between say 35 and 55 to represent the uncertainty of the amplitude of the amplitudes. So you can do that. So if you're concerned about it, then
But
to avoid this kind of overfitting, if you like, to the amplitudes that you have, you can specify the uncertainty. I'm not sure we've ever actually done that, to be fair. Oh.
We've lost you a little bit, I think. Hello? Yeah. I think your webcam takes too much of the broadband.
Oh, okay. Sorry, let me turn the webcam off.
Yeah, I think
I'll repeat. Is that okay now?
Yes, it's
right.
much
better. Right. Apologies for that. Let me repeat that answer. So you're right. So seismic amplitudes are part of the uncertainty. You know, we try and capture all the uncertainties as far as we can within ODiSI, and seismic amplitudes are one of those uncertainties. Typically for low chi angles, the uncertainties we'd expect to be fairly small, but as the angle increases, those uncertainties can get quite large. So there is an option in ODiSI to characterize the amplitude uncertainty as uncertainty in the chi angle, because if you change the chi angle, the amplitudes will change, and that's a way of expressing the amplitude uncertainty. So you might, for example, input a chi angle volume of 45 degrees, and you can put an uncertainty range on that of, say, plus or minus 10 degrees. And it will then randomly construct synthetics with a random chi angle somewhere between 35 and 55 to represent that uncertainty, the seismic amplitude uncertainty. And so that's a way of avoiding doing what you said, of kind of overfitting, putting too much reliance on the seismic amplitudes. And that will of course, will just show up, you know, as an increased uncertainty in the posterior, which is what is, you know, which is the correct way of dealing with it. I don't think we've actually ever used that option, to be fair. We kind of, you know, usually, but it is there. It is an option in there that you can, if you're concerned about it, we can run it with that characterization of amplitude uncertainties.
Yeah. So we have another, if all your wells are TD at the base of the reservoir and there is no well data from the underburden, what is the best solution in terms of zonation? So it's not a problem in ODiSI because you can create a rock physics model without having any well data. You can type the rock physics model without problem. So the only thing that you might have to extend the well just artificially, just to be able to see it in ODiSI. But it's, if you have the tool, it's something that we can show you as a support. I think we have another question. What is the cost in terms of time when using the Finesse option? So I did some tests. So if you use 10,000 pseudo well averaging 100, which is typically what we use here in Seagull within our service work for the regular ODiSI, if you use the same for Finesse, obviously it takes much longer. But the advantages of Finesse, it's you can you don't have to create 10,000 pseudo well. You can create 2,000 or 5,000 to have something similar and a very good output that reduce the residuals. So I would say there is no we have to test. You can quickly run 2D lines in terms of minutes. You have a 2D line with Finesse, without Finesse, with different pseudo well per trace. So Finesse might be a little bit longer, but I think because the results are much better, it's worth the time. Do you have any what are your thoughts on that, Pat?
No, I think you just summed it perfectly. Yeah, I don't have anything to add to that. Yeah.
So, do you typically use multiple seismic EI volume and or different seismic acquisition or processing vintages to address seismic uncertainty? So, it really depends on the data. If we have, if we are able to have one fluid angle and one or two lithology volumes, sometimes you can use two lithology volumes. So one that separates, let's say a typical example, shale and sand, and another volume that separates your tight sand from the rest, the two other. We can use 3 volumes. But so it's really depend on your data set. The thing that if you use multiple volumes, they need to have a very similar frequency spectrum, because ODiSI only use one Ormsby filter to create the synthetics. So all the synthetics created will have a similar frequency spectrum. So your input must have a similar frequency spectrum. I hope this answers the question. And we have some question about the licenses, but we will answer in a separate email.
Maybe we can just add something to the last one. I mean, the
Yes.
other reason for using multiple volumes is to allow you to distinguish more than 2 faces. Within a single window from a single seismic volume, you can only accurately distinguish 2 faces because otherwise there's ambiguity. If you have a third faces in the mix, then you get ambiguity. But if you can use 2 volumes, then that allows you to get an unambiguous distinguished 3 faces. So that's a really quite important reason if you can use an extra volume. Now, across the whole reservoir, you can quite often get away with several more than 2 or 3 faces, because you can separate them out more spatially within using the macro windows to separate them out. But within any given window, 40 or 50 millisecond window, you can only uniquely separate 2 faces from 1 volume, or 3 faces from 2 volumes.
So we don't have any more questions, but if you have any questions that you have during the day, do not hesitate to contact either your Seagull account manager or the sales team or the support team, and we will answer you. So as a conclusion, we want to thank you, our customers. We appreciate and welcome feedback, so please send that feedback. Should you wish to find out more about ODiSI or any other tool, please contact your Seagull account manager, or again, the sales or support. Thank you very much. And we have another session this afternoon if you want to have a look again at this webinar. Thank you, Pat, and thank you, Keegan. Have a good day.